What causes PID controllers to be sensitive to measurement noise? Imagine trying to steer a boat through choppy waters. The waves make it hard to tell if you're really changing direction or just riding the waves. That's similar to what happens inside a PID controller when measurement noise is present. PID controllers use three parts: proportional, integral, and derivative. The proportional part reacts to the current error, the integral sums past errors, and the derivative predicts future trends. But the derivative part is where the sensitivity to noise really kicks in. It looks at how fast the error is changing, so even tiny, quick fluctuations in the measurement can cause big changes in the control output. Think of the derivative as a speedometer. If the speedometer is very sensitive, even small bumps or vibrations can make it jump. When the measurement signal has high-frequency noise, the derivative amplifies these rapid changes. This means that small measurement errors, which are just noise, can be mistaken for real signals, leading the controller to react unnecessarily. In electrical engineering, the derivative term mathematically involves taking the derivative of the measured process variable or error signal. Since noise often contains high-frequency components, differentiating these signals makes the noise even larger. For example, a tiny high-frequency oscillation in the measurement can become a big spike after differentiation. This makes the control output fluctuate wildly, which can cause instability or wear on actuators. Another factor is that the ideal derivative transfer function increases gain as frequency increases. This means at very high frequencies, the controller becomes extremely sensitive to noise. To prevent this, engineers often add a low-pass filter to the derivative term. This filter reduces the high-frequency gain, but it also slightly slows down the controller's response. Measurement noise enters the control loop mainly through sensors and instrumentation. If the noise isn't filtered out, it directly affects the input to the PID controller. The proportional and integral parts are less affected because they respond to the magnitude and accumulation of error, not rapid changes. But the derivative reacts to these quick changes, making it the main culprit for noise sensitivity. Tuning the PID also plays a role. If the derivative gain is set too high, the controller becomes more sensitive to noise. Lowering the derivative gain can help, but it also reduces the controller's ability to predict and counteract future errors. Filtering the measurement signal before feeding it into the controller is another common approach. Using moving averages or exponential smoothing can help reduce the impact of noise. Excessive noise in the measurement can cause the control output to fluctuate rapidly. This can lead to unnecessary movements of motors or valves, causing mechanical wear and reducing system efficiency. This is especially important in electrical systems where precise control of power electronics or motors is needed. In practice, engineers balance the derivative gain and filtering to get the best response without amplifying noise too much. They often use a filtered derivative term, which includes a low-pass filter, to limit high-frequency noise. Adjusting the tuning parameters and adding filters helps make the PID controller more robust against measurement noise, ensuring smoother and more stable control.